Hello, my name is Aditya Indla, and I am a high school student from Bellarmine College Preparatory in California in the United States. Thank you for offering me the chance to present this project to you. In the United States, strawberry farming is labor intensive and time critical. Farmers need to harvest ripe fruit within 2 to 3 days, and the size of their farms makes it extremely difficult to accurately survey the farm and determine the optimal harvest time for strawberries. As a result, farmers employ fixed labor and pick their crop 3 times a week. This is very manual work, with laborers going around and checking each plant and picking the fruit. Farmers cannot accurately know the number of ripe and unripe strawberries, and so they cannot accurately plan when to harvest their crop, and they will thus employ a fixed number of laborers and pick fruits every other day. This means that, in the early season, there are too many laborers, but in later seasons, there are not enough laborers, and many strawberries go waste, up to 30%. If farmers can get accurate information on how many strawberries are ripe, they can plan their labor more dynamically. This leads to lower labor costs and fewer wasted strawberries. But the way to get this information on ripe and unripe strawberries is challenging, and machine learning can help solve this problem. Machine learning is more accurate at identifying variations and patterns over human beings, and using machine learning, farmers can survey large farms without needing large numbers of people, leading to a more scalable solution. The learning algorithm is also continuously improving, with each dataset fine-tuning the quality of image recognition further and making it more accurate. Finally, the image recognition model can be further trained to recognize other situations, like plant health, weeds, fruit sizes, and other situations. But why can't we use existing models? Current models are massively inaccurate, as they have been trained to work with generic images, and not specifically strawberries. For example, consider these four models. The first model only identifies one strawberry, labeling it as an apple, which is obviously incorrect. The second model failed to identify anything. The third model identified a large number of items, but very few, if any at all, were actually strawberries. Instead, it misidentified them as bananas, broccoli, people, elephants, and even apples. And the fourth model failed to find any strawberries either. From this, it is clear that current off-the-shelf models are not effective at solving the current problem. And so, our solution is to create a custom image recognition model that identifies strawberries and categorizes them based on their ripeness with high accuracy and precision. So, let me walk you through how our proposed solution categorizes strawberries into ripe, semi-ripe, and overripe fruits. First, a drone or some other survey mechanism takes pictures of the plants. The images are then fed into the custom-built TensorFlow model, which labels ripe strawberries as strawberry 100%, semi-ripe ones as strawberry 50%, and overripe ones as strawberry plus 100%. The system then reports the percentage of ripe strawberries to the farmer, allowing them to better determine the amount of labor required to effectively pick their farm. Let me walk you through the framework and models we used in our project. And the first basic framework is TensorFlow. TensorFlow is the open source framework for machine learning and deep learning developed by Google. It was released in November of 2015, and it's used in many situations for classification and prediction. It runs on Linux, Mac, iOS, Raspberry Pi, and Windows, and the Python API provides a large number of powerful computational neural networks for anyone to use, and there has been an extensive amount of research to develop these machine learning models. And TensorFlow also has a large developer community continuously improving the framework, making it the most ideal framework to use to build a machine learning model on. And there are many next-generation companies that use TensorFlow to solve key challenges using machine learning. For example, PayPal uses TensorFlow deep learning to improve payment and fraud detection rates while identifying legitimate uses better. And because of these extensive capabilities, we chose to implement our solution with TensorFlow. Let me also explain the two machine learning models used in our solution. The base deep learning TensorFlow model used by our project is an inception convolutional neural network module. A convolutional neural network is a deep learning algorithm which can take in an input image, assign importance to various aspects or objects in the image, and be able to differentiate one from the other, and these are called features. This model then categorizes those various features of the picture, especially those of a farm in our case, such as edges, colors, and gradients in the first layer. Deeper layers of the network identify other features to the more granular level, creating feature maps. And inception is one of the most efficient CNN models, especially for image processing and object detection. In conjunction with the inception CNN model, we also use the SSD object detection model to identify strawberries and also report how confident we are about their detection. Images are first run through inception to identify and extract the features. Then, a large data set of images is marked with bounding boxes that indicate ripe, unripe, and overripe strawberries. The model was trained on these images in order to learn how each type of strawberry looks. Then, when the image to be classified is presented to the model, it creates a bounding box over the key features and compares with pre-trained features. If there is a match, the bounding box is presented with the match and how confident the model is of the match. And we use these frameworks and these models to create our solution. So, how do we train this model? Well, we train this model in a three-step process. First, test images are taken by recording multiple strawberry farms under different light conditions during different times of the day. They were recorded in 60 FPS 640 by 480 resolution or 30 FPS 1280 by 720 resolution using the Intel RealSense D415 camera. Secondly, images were labeled with the label IMG tool as ripe 100%, semi-ripe 50%, or overripe plus 100%, and the label IMG tool produced .xml files to train the custom model. However, TensorFlow needs a specific file type, the TF record type. And so, to convert the XML file to TF record, first the file was transformed into a .csv file to store the raw data. Then, the CSV was converted to TF record using a Python program. Training images represented around 80% of the labeled images, and testing data represented the other 20%. After the models were trained, these are the following results of what happened. The first trial was with a model trained over 3,000 intervals, and it was very inaccurate. As you can see, it identified leaves as strawberries and couldn't identify even a single strawberry exactly. This is likely because green strawberries were included in the training set in this model as strawberry 0%, and the presence of these green strawberries confused the model as it thought the leaves were also strawberries, and thus the leaves were labeled as unripe strawberries. In the second trial, the model was trained over 4,000 intervals. Here, the training data did not identify unripe or overripe strawberries. Instead, all strawberries were consolidated under one label, with completely unripe strawberries, or strawberry 0%, being taken out completely. This model was somewhat more accurate, but it was still unable to identify many of the strawberries, still leaving them completely unidentified. And this would also not provide enough information to farmers. It would only tell them they have a certain number of strawberries available, not how ripe the strawberries are and how ready they are to be picked. The third trial was the most accurate trial of all the models trained. This model was trained over 25,000 intervals, and it was trained on a larger dataset. They included ripe, semi-ripe, and overripe strawberries separately as the 50%, 100%, and plus 100% categories, respectively. This was far more accurate than either of the two previous models, especially when it came to the plus 100% strawberries. However, it was still somewhat inaccurate when it came to the 50% and plus 100% models, mostly because there was a lack of data of these specific types of strawberries. Additionally, shadows from the tarp may have also influenced the model, especially when it came to the plus 100% strawberries, because they often blended into the black tarp with a shadow falling over them. These four images provide more examples of how effective this third trial of the model was. Almost all of the strawberries in this image that are greater than 50% are categorized, and plus 100 strawberries are somewhat accurately identified with a couple missing. There are very few 50% strawberries, and most of them are identified, but some are still left unidentified. When it comes to 100% strawberries, almost all of them are identified and with high confidence too. And this proves the viability of using this model in order to provide more information to farmers. And so, in conclusion, the proposed solution was effective at identifying ripe strawberries, and it serves as a good basic system for farmers to use. However, many further improvements can be made to this project to produce a report that can count the number of strawberries and provide a percentage that is fully ripe. The model can also be further trained to more accurately identify unripe and overripe strawberries by visiting more farms and gathering more data during early and later seasons when more strawberries are semi-ripe and more are overripe, respectively. Thank you for your time and attention as I share our proposed AI-based farm survey technique for efficient fruit harvesting. I would like to thank Dr. Anish Sharma for his help in guiding me through this project, and I would also like to thank Dr. Wang for presenting on our behalf. Thank you once again.